Hello, class. Okay, so this lecture we're going to talk about heat and energy. Now we talked about heat before. Now we use the letter Q for heat. And really heat is just a form of energy. So say we have an object here, we can add heat to this object. So if energy flows into it, you can say heat is added to it. So if we put this object, say, in contact with something at a higher temperature than it, heat is going to flow into it, or energy in the form of heat is going to flow into this object. Similarly, if we place this object in a colder environment, heat is going to flow out of the object. And so we actually have to distinguish these two cases. Let's say we have two objects, A and B. And let's say A is at a higher temperature. So heat is going to flow from A to B. Now it's the same, like say 1,000 joules of heat flows from A to B. Q is going to be the same for each object, except A is losing energy and B is gaining energy. And so we accept this convention that for A we say Q is less than 0, and for B, Q is greater than 0. So this is just a convention. If heat is leaving the object, like it's leaving A, we say Q would be like, say, minus 1,000 joules, or for B, Q would be plus 1,000 joules. So it's just an energy transfer, same amount, nothing's escaping that system, A plus B. But we have this convention depending on which way the heat is going. Now I should point out this is our convention. This is what our book uses. Different books actually use the opposite convention. So you might see somewhere like here Q is positive if heat is leaving the system, for instance. Some books do that, and so you might get different equations based on that different convention, but this is the one that we use. So Q is heat. Another thing is internal energy. So what is internal energy? Well, this object is made up of molecules, or in some cases atoms, if you have an element like just a block of iron. But the whatever is making up this object, those particles have energy. Internal energy, they have kinetic energy because they're moving around. Now, in a gas, for instance, these things are physically moving around. Like the air in the room is literally just moving around. It could be bouncing off walls, but it's moving rather quickly, we'll find later. But in a solid, when the molecules are kind of fixed in place, they oscillate though. And if you just add up the energy of all the parts of the system, you get the total internal energy of the object. So there's a difference between heat and internal energy. Internal energy is just, this object is made up of things, atoms or molecules, and if you just add up all the energy of all the parts of it, you get the total energy of the object. Heat is a flow of energy from one place to another. So there are different things. Kind of an example. Let's think of an example. Say you have a large block of ice. and you have a cup of water at room temperature. Now, the question is, which of these has more internal energy? The answer is probably this block of ice. Now, the ice is cold. It's got to be at least 0 degrees Celsius. We're talking about normal conditions here, where the water is at room temperature. And so the water molecules, so again, these are both water, just in different states. Here, the water molecules have more energy because it's at a higher temperature. However, this block of ice is bigger, and so there's just more molecules. So when we talk about the internal energy of this block of ice, we're adding up all of the molecules in the block, and there's a lot more than this glass of water. So even though, on average, like each individual molecule here has more energy, on an individual basis, just because of the size, this block of ice has more internal energy. Say we have a glass of boiling water. So let's forget about this block of ice. Let's just say we have a glass filled with boiling water. So there's steam coming off of this. Now, it doesn't really make sense, again, maybe in kind of a common English, you might say there's a lot of heat here, but really in physics, it would be more accurate to say there's a lot of internal energy here. Heat is only used to describe a transfer of energy. Now again, if this is glass of water is sitting in the environment, there would be heat flowing from the water to the room because the room's at a colder temperature. But for us talking about the water itself, it has a lot of internal energy. So we don't use, there's a distinction between the terms internal energy and heat. Just be more accurate to say this has a lot of internal energy and just restrict the word heat to mean energy that's flowing from one system to another. So again, they're both energy, they're both measured in joules. It's really just about how we're talking about these things. Okay. Now we talked about states of matter a little bit. There's 3 basic states of matter. Solid, liquid, and gas. Now again, there are more states of matter than this. Things like plasma, that's another state of matter. But ordinary matter is going to be in these states, either solid, liquid, or gas. Water is a great example because we're familiar with all of those. Solid water is just ice, liquid water, just water. Most substances, we don't have different names for the different states of matter. But water vapor, there's also water vapor in the air. So that'd be the gas form of water. So you probably have all 3 forms in your house. If you have ice in your freezer, you've got all 3 states of water in your house. So a very common one. Now generally, what is the difference between these? And again, we have to look at the molecular level. Solids generally are this is what happens when you have a low temperature. So again, say we have a solid. Let's stick with water. So say we have a block of ice. So it's made out of molecules of, let's just say it's pure ice, just H2O. So there's molecules here. And normally molecules, there's electrical interactions between molecules. And so there can be this attraction between them. And they want to kind of settle in, and we say their lowest energy state. Things tend to want to go into their lowest energy state. You're going to have to, say you have a ball on top of a hill. This ball has a lot of energy up here because of gravity. It has potential energy. If you nudge it a little bit, it's going to fall and keep falling until it reaches the ground. That's the lowest energy state that it can be in. And that's where things tend to go. What's giving it energy is gravity. So gravity wants to pull it down to its lowest energy state. Similarly, these interactions between the molecules, or just in solids in general, they form structures where there's all sorts of different structures for different kinds of matter. Like if you look at like iron or copper, they can have different structures, but the atoms arrange themselves in some regular repeating pattern. And at low temperature, they're able to do that. So that just this electrical interaction between the atoms or molecules, they form this regular structure. Like if you could see the molecules, they form these regular patterns, where they all have their place. However, the atoms and molecules they have energy that causes them to vibrate. So like if you look at any molecule, it's vibrating around its kind of place in this lattice. And if you heat up the object, they gain these molecules, you're adding energy to it, and these molecules oscillate more rapidly. And eventually, they can't really hold themselves together. So they're still stuck in this, they still kind of stick together, but if you heat this up enough, these molecules have enough energy they can break free from like their location, and they can move around fairly easily within this, like say we put this ice in a glass. So the molecules, once we heat it up, they have so much energy we can't really hold them together in a fixed place, and they're still free to move around. Now the water itself is going to be in this container. It usually stays together, but the water molecules don't have like a fixed location in the sample. And then if we keep heating it up, they can gain so much energy. So let's say we turn this into water. Again, these water molecules are pretty much fixed. So again, if you just follow one molecule, it can wander around in here, but it's still stuck, in this container. But if we keep adding heat, what's going to happen is some of these molecules have enough energy that they can kind of just leave and go shooting off. They can't be held together any longer. They have enough energy that they're freely moving. Now, again, say this was a glass of water in the room. It might be stuck in the room. It'll hit the walls of the room and bounce back. So it's just in a bigger container now. But in a gas, the molecules don't really interact with each other very much, unlike in a liquid. And so those are kind of a basic idea behind the three common states of matter. And so again, at the lowest temperature, things tend to be in their solid state. And then if you raise that temperature, you get a liquid state. And finally, high temperature, you have a gas. Okay. And again, different materials will the kind of transition from one state to another. That'll occur at different temperatures for different materials. Now, let's say we start out with something that's very cold. Let's say we have ice at minus 20 degrees Celsius. Okay, so we have ice that's very cold. This is definitely going to be in its solid state. And what we're going to do is add heat to it. So let's say Q is the heat added to this ice, and here's our temperature. We'll say in degrees Celsius. So this would be heat in joules. And we're starting out at minus 20 Celsius, so let's say that's here. Now what happens when we add heat? First thing that happens, I'm going to lower this a little. Okay, so the first thing that happens we add heat is the temperature is going to increase. Okay, so we're going to have temperature increases until we get to 0 degrees Celsius. And you're going to write this down for water. We already know that the freezing point is 0 degrees Celsius, and the boiling point is 100 degrees Celsius. I don't want to put a dash there. That looks like a minus sign. Guess it doesn't matter if we have minus 0 Celsius, but okay. So here we're at minus 20, and then we know up at 100, that would be the boiling point. Okay. So again, once we heat this up to 0 degrees Celsius, so basically just looking at these values, here when we're below 0, or at 0, that's like in its solid state, and between 0 and 100, ice is a liquid, and above 100 degrees, it's going to be a gas. And again, these are kind of like standard values. It depends on pressure as well. We're saying normal atmospheric pressure here. And so what happens when we get to 0 degrees Celsius? It's going to start to melt once it reaches 0 degrees. Or we might be more familiar with the boiling point, where say you put a pot of water on the stove and turn up the heat. Say you had a thermometer in the water. And what you'd see, it's going to get to the boiling point. Eventually the water is going to boil, but from experience that takes a fair amount of time for that to happen. It can take several minutes. So you're adding heat constantly, but it takes a long time to boil. And so you have to raise the temperature up to that 100 degrees. But what happens if you keep the flame on and you've got this pot of boiling water? And you're continually adding heat to it, but if you had a thermometer in that water, you would see that the temperature is not changing. And so that's going to happen here as well. So we keep adding heat, and the temperature is going to remain at 0 degrees for a while. And then once we have enough heat, okay, so what happens? We have ice here. This is in its solid ice form. And once we get to 0 degrees, we're continuing to add heat, and what this heat is doing is it's melting the ice and turning it into water. So from here to here, we have a mixture of ice and water. Where at this point, it's all ice, and now as we add heat, some of that ice is melting and turning into water. And again, the more heat we add, the more water we're getting, the less ice. Eventually, we've melted the entire block of ice. And so now we're purely in a liquid water state. And then we add heat and the temperature increases now up to 100 degrees Celsius. And then the temperature levels off again. So here we're in a liquid state. And here we're in liquid/gas. So again, we've got, say, our pot of boiling water. It's purely a liquid now, but it's reached 100 degrees. So again, you know that it reached a state when bubbles form in the water, then they can rise up. Talk a little bit more about that later, what's actually going on there. But, so we've reached this boiling state here. And again, if you leave a pot of water on the stove long enough, and come back and check it later, all the water could be gone. It all evaporates. So it doesn't disappear, it turns into gas, which then leaves the pot and goes wandering around the room. And so here it's all liquid. Here all the water has been, we call this vaporized. It's turned into gas or evaporated. And so now we're purely in a gas state, and if we continue to heat it, then temperature will continue to rise. So this is an overall picture of what happens if you start with something that's very cold and just keep adding heat. First you get a temperature rise up to this point at 0 degrees Celsius. So I should really call this a freezing or a melting point, because this graph, we could very well go the other way as well. Here we were adding heat, but again we could follow this backwards. If we have a gas and we remove heat, eventually it's going to condense into this liquid state. And then it'll freeze into a solid state. So again, like here, we're going from a solid to a liquid state. So this is actually like a melting point. And this is a boiling point, but it depends on which way you're going. It's either a freezing or a melting point. If we're going this way, it's melting. If we're going this way for removing heat, so we start out with liquid water and then it freezes at that temperature. So again, freezing, we could call this freezing / melting, and this is boiling or condensing point. Okay, so this is an overall picture. Looks at like the states of matter for one particular substance, water. And this is a fairly typical picture. Now, so basically what happens when you add heat to a substance? One of two things is going to happen. You're either going to get, like here, we have a temperature change. So we're adding heat, and that's causing a temperature change. And here are these horizontal lines. There's no temperature change. Here, these are phase changes. So if you look at these horizontal lines, those are phase changes. Because the temperature is constant here. So what's this heat doing? Well, it's causing it to go, in this case, from a liquid to a gas. So remember, the gas molecules have more energy than the liquid molecules. So you're adding energy to it, and that's giving those molecules enough energy so that they escape, but you're not causing a temperature change. So there's two things we need to talk about here. Phase changes and temperature changes. So one of these two things is going to happen when you add heat to something. Okay, I'll write this down over here. Let's look at a phase change. I'm just going to write down the equation, and then we'll talk about what this is. So first off, we want to look at the types of phase changes that are possible. So we've got three states of matter. I draw it like this. Say a solid, liquid, and gas. So it's possible to change from any state to any other state. So let's say we go from a solid to a liquid. That's called melting. Think ice turning into water. Liquid to a solid, that is freezing. Now say we have a liquid turning into a gas. That's called vaporization. So liquid to a gas, that is called vaporization. Now a gas turning into a liquid, that's called condensation. Now it's also possible for a gas to go directly into the solid state. And that's also called condensation, or condensing. So, just have that one word in the middle. And finally, for a solid to go directly into a gas, this is called sublimation. Okay, so these are the three common states of matter, and these are the types of transformations that can occur between them. And again, this is kind of common for all materials, that these can all happen. Okay, now let's go back to this equation, Q equals mL. So Q is the amount of heat either added or removed from the substance. Now, what is L? L is called the latent heat. I'm going to write that here. So L is called latent heat. And there's actually three types of latent heat. Although only two we're really going to use here in this class, I'll list them all. We have LF. This is the latent heat of fusion. I'll just write them all down and then explain what they are. Okay, so LV is the latent heat of vaporization, and LS is the latent heat of sublimation. And again, the latent heat depends on what type of phase change we're talking about. So if we're going between solid and liquid, so if we're melting or freezing, we'd use the latent heat of fusion. If we're over here between like a liquid and a gas, that'd be latent heat of vaporization. And between a solid and a gas, we use latent heat of sublimation. And again, it doesn't matter what direction you're going. So say you have a block of ice and you add, say, 1,000 joules and melt it, turn it all into water. If you want to turn that back into ice, if it took 1,000 joules to completely melt it, it would take 1,000 joules to refreeze it. So you add 1,000 joules to melt it, you'd have to remove 1,000 joules to freeze it. It's the same number, just going in different directions. So again, whether you're melting or freezing, you use latent heat of fusion. Over here, you use vaporization, and over here, sublimation. Whether you're going from solid to gas or gas to solid. So we're going to say ML. So Q is heat, M is the mass. So again, say you have a pot of water that's boiling. It's 100 degrees Celsius. If you add a certain amount, like say you add 100 joules of energy, you're not going to just vaporize the entire pot full of water at once. The more heat you add, M is like the amount that's going through the phase change. So if you have a pot of boiling water, it doesn't just instantly evaporate. You have to add a lot of heat to get it to fully evaporate. Say if you have like an ice cube, you take out the freezer, set it on the table, it's not going to just instantly turn to water. There's heat flowing in from outside, but again, a given amount of heat can only melt so much. So that covers phase changes. Maybe we should put an absolute value sign there around Q, because Q can be positive or negative depending on which direction the heat is going. So I guess technically we should have a Q there, because M, mass, that's positive, latent heat is positive. Just some numbers for water. We have latent heat of fusion and latent heat of vaporization. I don't remember these numbers, see if I have them written down. Yeah, for water, for fusion, 33.5 times 10 to the 4th joules per kilogram. And 22.6 times 10 to the 5th joules per kilogram for vaporization. So it takes a lot more energy to vaporize water than to freeze it or melt it. It's much easier to melt something than vaporize it. Okay, so yeah, that's it for phase changes. They happen at these particular temperatures, and again, these values depend on the substance. Like water at normal atmospheric pressure, it'll freeze or melt at 0, and it'll either boil or condense at 100 degrees Celsius. And so if you're at the temperature, if you're adding or removing heat, this will tell you like how much of that goes through the phase change. Okay, so now we want to talk about the other thing that can happen when you add heat to something, and that is a temperature change. So if you're not at one of these temperatures, if you add heat to it or remove heat, you're going to cause a temperature change. And I'm going to write down the equation. Maybe instead of just writing down the equation, we should kind of reason this out. Obviously, let's look at delta T. So forget that equation's there for a moment. What I'm going to say might be a reasonable assumption is that the changes in temperature is inversely proportional to the mass. So like, again, say you've got two containers filled with water. Like one is 100 grams, the other is 1,000 grams or a kilogram. If you add the same amount of heat to each of those two systems, the smaller one's going to heat up a lot more. So they're both absorbing the same amount of heat. You're getting a much bigger temperature change for the smaller object. So a more massive object, the smaller the change. Hopefully that's reasonable. And also the change in temperature is proportional to the amount of heat that you add. So if you add twice as much heat, you get twice the temperature change. Now again, this statement is not exactly true. Like 100% true. It's more of a pretty good approximation. So in general, this relation, it kind of depends on what temperature you're at, but it doesn't depend significantly enough for us to worry about it. Like earlier when I had that graph, let's draw it over here, like a real short version. Say you go from like here. So again, this was temperature, this is Q. So this was 0. So we had ice, it melted, and then we have a temperature change. So basically what this relation is saying is that we have a straight line here. Now if you were to actually plot this like real data, there might be a tiny amount of curvature, but not enough for us to worry about. I will say one more thing about this though. So it doesn't depend on the temperature, but it does depend on the state of matter. But I'll come back to that. Okay. And also the change in temperature also depends on the actual material itself. Like if you have water and mercury, like same mass, add the same amount of heat, you'll get very different effects. The mercury would have a much greater temperature change. Water has a very what we call heat capacity. That's what this C is. So again, if we put this together, we get this equation where C is our proportionality constant. This is called the specific heat or specific heat capacity. And this L here, this is latent heat. So again, C depends on a material. Now, let's look at water. This is a very important one here. The specific heat of water is 4186 joules per kilogram Celsius degree. So again, that's just for water. And that's water in the liquid form. For ice, it's around 2,000 joules per kilogram Celsius degree. So this is water. That one is ice. Okay, so very big difference between like frozen water and liquid water. But again, if you heat up this water from 0 to 100, this number won't change enough for us to care about, starting at 0 and going to 100. So like I've got this table in the notes. I won't write them down, but for water, again, this was water at 15 degrees Celsius. So if you change to a different temperature, you'll get a slightly different value. But again, we don't care. But just for comparison, mercury is 139. So that's a huge difference between water and mercury. And again, that's why mercury is used in thermometers. You add heat to the mercury, like so you want to take your temperature, you're warmer than room temperature, and so heat's going to flow from you into the mercury. And again, because this number for mercury is so small, you're going to get a large temperature change, which will cause it to expand. If you tried to make a thermometer out of water, that would be much more difficult to do. Take a lot more heat to cause that any noticeable effect. So yeah, mercury is also kind of an extreme. But if you look at different liquids, I've got benzene, 1,740, ethyl alcohol, 2,450. That's the biggest one on the table outside of water. So around 2,450. So again, water is almost twice as much, the next highest liquid on this thing. And again, for ice, we have 2,000. Like other solids, like lead is 128, silver 235. So again, just overall, water has a very high heat capacity. It takes a lot of energy to change the temperature of water. So a very unusual substance there. All right, so yeah, that's actually it for, so basically we just talked about the different states of matter and changes between them. So yeah, that's it for this one.